It's easier to describe the final. Essentially, you take it's 4, 1, 3, something. It's closer to 4. So I just 1024. Yeah, so they got the first digit. There are examples. So anyone else?
We just talked about the arithmetic.
So
Yeah, I teach tomorrow. It's like 11 tomorrow.
we're not when we
So, Friday morning I'm looking for take care of on Friday morning, so I'll be like borderline if I get here at 5:30. I agree. Almost nothing.
Yeah, themselves for themselves.
The proof is essentially unreadable after the first page.
But it's on light. One can think about this argument. Upper bound independent operator.
Okay, so we are ready to continue, and the next last speaker for today is Laszlo Lovasz, and he will tell us about the arithmetic removal for triangles and K-cycles.
Thank you very much, and thank you for inviting me to speak. So this is joint work with my former advisor, Jacob Fox, who's not here, just arrived, and his other student, Lisa Sauermann, who's also here at the conference. So I'm going to kind of give some background, and then I'm going to say what this arithmetic removal lemma is that Ben Green proved, and that we proved new bounds for, and I'll try to give some idea of the proof for triangles. Then I'll try to give some idea of the proof for K-cycles, which is different, and I'll try to give some idea of why the same proof doesn't work. And then I'll discuss lower bounds on the exponent and mention some further questions. So first, let's talk about something that's non-arithmetic, the graph removal lemma. So what this says is the following. So if you fix a graph H, and you have a positive epsilon, then there exists a positive delta, such that if you have any graph on n vertices that has a small number of copies of H, so it moves delta times n to the v of H, then you can remove a small number of edges, less than epsilon n squared, to make it H-free. So here you could theoretically have n choose VH, or roughly n to the power of VH copies, and instead we have a very small density of H. And this was proved by Ruja and Semeri for triangles, and then it was stated by Allen, Duke, Lefman, Riddle, and Yoster for general graphs. And the proof of this was basically using the regularity method. So you apply the regularity lemma and use the counting lemma, and then prove it. I don't want to go into the proof. But so this is a very important use of the regularity method, and this has many applications in extremal graph theory, additive number theory, in theoretical computer science, and discrete geometry. So one statement you can apply it to is Roth's theorem. So this is a theorem that says that if you have a subset of the integers from 1 to n, that has no three-term arithmetic progression, then the maximal size of this set is little o of n. So the maximum possible density goes to 0 as n goes to infinity. It doesn't give the best bounds for the theorem, but it still gives a proof of it. Now Roth's proof gave a bound of the form n over log n, and the best known bounds are all of the form n divided by log n times smaller order terms due to Sanders and Blue. On the other hand, the best lower bound construction for Roth's theorem is due to Barron, which gives a lower bound of the form n over e to the c root log n. So it we know it's little o n, and this shows that it can't be n to any power smaller than 1. But besides that, there's still a very large gap in kind of understanding the maximum size of this set. And one reason I want to mention this in particular is that this gives a bound in the triangle removal lemma for graphs. So for removal lemmas in general, I like to think of 1 over delta, which is the density of whatever you're looking at. I like to think of bounding 1 over delta as a function of 1 over epsilon. So that when I say upper bound, it means, what I'll mean is I'm giving an upper bound on 1 over delta as a function of 1 over epsilon, which is kind of proving something good, and then giving a lower bound is kind of giving a construction saying that it can't be that good. 1 over delta has to be big enough, so delta has to be pretty small still. And so this gives the best currently known bound for the triangle removal lemma, showing that it's super polynomial, although barely super polynomial. Okay, so now let's move to the arithmetic setting. So let me state Green's k-cycle removal lemma. So for this, let's call a k-tuple of numbers in, so we have fp to the n, our kind of base set, and we call a k-tuple of numbers a k-cycle if their sum is 0. And then the arithmetic k-cycle removal lemma is a natural analog of the graph removal lemma. So for any epsilon bigger than 0 and k, there exists a delta such that if you have k subsets in fp to the n, and then you look at the k cycles between the sets, so in their cross product, so you could theoretically have as many as n to the k minus 1. If each set is all of fp to the n, then you have big N choices. Here big N, so here throughout this talk, big N will be p to the n, the size of this base set. So you have k minus 1 degrees of freedom here because you could choose anything for the first k minus 1 and then the last element is fixed. And here if it's much smaller, so the density is very small, then we can delete less than epsilon times n elements from each xi to remove all k cycles. Okay. So Green's proof actually works for general finite abelian groups. And he basically develops an arithmetic regularity lemma using Fourier analysis and uses that to prove this. Now it turns out that this also follows from the graph removal lemma. So this is an argument due to Kral, Serra, and Vena. You need a directed version, but once you have the proof for non-directed, you can also adapt it to the directed version. So let me give a summary of the Kral, Serra, Vena proof. I'm going to go over it for triangles, but it works exactly the same way for k-cycles. So we have three sets x, y, and z. So again, we have the property that we have at most delta times n squared triangles between them, and then we want to argue that we can remove a small number of points from each of them to get rid of all triangles. So we define an auxiliary graph. We take three sets of vertices, each corresponding to fp to the n, and then if we have points in the sets, so between the first two, we connect a pair of vertices if their difference, if u minus v is in x. Between the second two, we connect them if their difference is in y. And between the last two, we connect them if their difference is in z. So then it's easy to check that a triangle in our original sets corresponds to n triangles in this graph. You can choose this point arbitrarily, and then it's all fixed.
That's not the separately order construction.
What is this?
Okay. So any triangle corresponds to, it corresponds to big N triangles in the graph. And conversely, if you have a triangle in the graph, then it comes from such a triangle in x, y, and z. And so there are at most delta n cubed triangles. We had delta n squared originally, and each one gets big N. So then we can remove a small number of edges from this graph to get rid of all triangles. And then if we remove from x, y, we remove a point from x if at least n over 3 of the edges corresponding to it are removed in the graph, and same for y and same for z, then you could, if you think about it for a moment, you can convince yourself that you must end up getting rid of all triangles. So in this way, we've shown that the graph removal lemma implies the triangle removal lemma. Let me briefly just discuss kind of another way of thinking about removal lemmas in general. Again, I'm going to concentrate on the triangle case, but this works for k-cycle removal, this works for graph removal, and it's really almost a rephrasing of the problem. So here, let's say that a triple of functions, and we're thinking of these as the characteristic functions of our set. The triple is triangle free if you don't have a triangle that has a property that x is in F1 in the first set, y is in the second set, and z is in the third set. And then we say that this triple is epsilon far from being triangle free if not only is it triangle free, but we cannot modify it on a small fraction of the elements to make it triangle free. Okay. And then we kind of want to test, if we have three functions, we want to efficiently test whether they're kind of differentiate the two cases when they're triangle free and when they're far from being triangle free. And kind of in the middle, then it's okay if we make a mistake, but if we're not in the middle, we don't want to make a mistake, at least not with high probability. And so using the arithmetic removal lemma, we can actually come up with a method of testing whether a triple of functions is triangle free or epsilon far from being triangle free. So the reason is that if a triple is epsilon far from being triangle free, then there are at least delta times p to the n squared triangles, because if you want to make it triangle free, there's no reason to change zeros to ones, so you would just be changing ones to zeros, and then it's exactly the condition in the removal lemma. And then you can just start sampling random possible triangles and checking whether they're always in the corresponding set. So since we have a lot of triangles, if we sample R random possible triangles, so if we see a triangle, then obviously we know that we're not triangle free. But if if we don't see a triangle, then we can safely guess that it's far from being triangle free. Sorry, that it is triangle free. If we are epsilon far from being triangle free, then the probability of never seeing a triangle after R guesses is 1 minus delta to the R, and then if R is, say, 10 over delta, then this is very small. So here the point is that the number of queries that we need depends on delta as a function of epsilon, but it doesn't depend on n. And so if you get bounds for the removal lemma, then that gives you bounds on the number of queries needed in terms of epsilon. And here again, upper bounds on 1 over delta and the removal lemma give an upper bound on the number of queries and vice versa. And so the natural question is, so we know that we can test with some number of queries that only depends on epsilon, but can we test it in polynomial in 1 over epsilon queries? And this is basically, on some level, equivalent to the removal lemma, but it's another way of thinking about it. So what bounds do we get for the arithmetic removal lemma? So in order to discuss the original bounds, we need this tower function, since it uses regularity. So let t be a tower of 2's of height n, t of n be a tower of 2's of height n. So t of 1 is 2, and then t of n plus 1 is 2 to the tn. And this, if you've never seen this function, you should know that this blows up very, very quickly. So if you just take t of 5, that's already 2 to the 65,000. And Green's proof of his removal lemma gives a bound on 1 over delta that's a tower of 2's of height polynomial, a power of 1 over epsilon. And we have similar bounds for the graph removal lemma, which also uses regularity. So using the Kral-Serevena proof, we get the same type of bound. And so, and Green asked, can we improve the bounds on this in the arithmetic setting? Now, so after the Kral-Serevena paper, Jacob improved the bound on the graph removal lemma. For any fixed graph h, you can get a bound on 1 over delta. Instead of a tower of 2's of height polynomial 1 over epsilon, it's log 1 over epsilon. Depending on your point of view, this is a huge improvement over still a tower function, but it's definitely smaller for any epsilon. And then by Kral-Serevena's proof, we get the same bound for the arithmetic k-cycle removal lemma. So tower of 2's of height log 1 over epsilon, constant depending on k. So what do we have in terms of lower bounds? So for k equals 3, Bhattacharya and Shi gave a polynomial lower bound on 1 over delta, so it's 1 over epsilon to some power, roughly 4.847. And then this was improved a few years later by Fu and Kleinberg to 1 over epsilon to roughly 13.239. So this is all in f2 to the n, and k equals 3, this special case. And until recently, this was kind of the state of the art. So, for example, if we just look at f2 to the n, we had this polynomial lower bound and tower type upper bound. So our result, the first result that I'll mention with Jacob is for k equals 3, we prove a polynomial upper bound for Green's triangle removal lemma in fp to the n. So for p equals 2, the exponent we get is the same number 13.239. So it's the same number I had in the last slide. And for p at least 3, we also obtain an explicit constant in the sense that, so we prove it for an explicit CP3, and we can show that this is a type by a result of Kleinberg, Sauermann, and Speyer. And then for k-cycles, so the truth is we kind of assumed this should easily go through for k-cycles, and then when we tried to do it, it turns out it doesn't. But now we can also prove a polynomial bound for k-cycles with Jacob and Lisa. So for any prime p and non-negative integer k, we have an explicit CPK such that we have a polynomial upper bound in the removal lemma. And but this is not necessarily sharp. Okay, so let me first discuss the proof for triangles. So we use the recent breakthrough results on cap sets and three-term arithmetic progression. So let me summarize these results. So as we saw yesterday, Krug-Lepach proved gave an exponential improvement on the maximum possible size of a 3 AP free set in Z4 to the n. And then Ellenberg and Heisweit use their method to prove a similar bound in FP to the n. And then Blasiak, Church, Cohn, Grashow, Laszlo, and So, and Umans, and independently Alon, Noga, showed that the same bound actually holds for a more general problem, the multicolored sum free problem. So basically here, instead of one set, you have 3 different sets, and you have the property that you've paired up or tripled up, matched up the elements, so that in this matching that you have, the triples sum to 0, so they form a triangle, but you have no other triples between them. And so why is this a special case of this? Well, if you take x and y, or let's say take x and z to be a, and y to be minus 2a, then this bound gives you a bound on this. And really for this problem, you could, well, if p is odd, you could write minus 2 here instead of 1, and it would be equivalent. So this is really, for odd p at least, this, except you have 3 different sets instead of a single set. That's the right way to think of it. And in fact, for the multicolored sum free problem, this bound is sharp, at least the exponent is sharp. And this actually follows in F2 by the construction of Fu and Kleinberg that I mentioned earlier, which also shows that the removal lemma in F2 is sharp. And based on work of Kleinberg, Sauermann, and Speyer, we also have a sharp bound for in FP instead of F2. Okay. So really, I just need this, the bound on the multicolored sum free problem. I'm just going to need that as a black box for our purposes here. So remember this if you forget everything else on this slide. Okay, so now let's give a sketch of the proof. So here's the statement again. So we want to show that for every prime p, there's this explicit CP3, such that if you have less than epsilon to the CP3 n squared, so this is our delta triangles between the sets, then we can delete less than epsilon times n points from each of the sets to remove all triangles. And actually what we show is the following statement. So the basic observation is that the number of points you need to delete from each of the sets is within a factor of 3 of the maximum number of disjoint triangles you can take. So an equivalent problem is saying that if 3 sets have epsilon times n disjoint triangles, then there are at least epsilon to the CP3 n squared triangles kind of between them. So this implies this, because if you just start taking disjoint triangles greedily, and if you can't take any more, then you just delete all the points in the triangles and you've removed all triangles. And then you can also convince yourself that up to a factor of 3, you can also go the other way. So basically this is our goal. So if we have epsilon and disjoint triangles between them, then we must have a lot of triangles in total between them. And in fact, we can even weaken our goal slightly. So if you recall yesterday in Peter Pak's talk, there was this product construction that once you have a small construction, you can take a product and get a construction arbitrarily large dimensions. In art, we can also do the same thing here, and what that basically means is if you can prove this with little o1, you can also prove it without little o1, because if you had a small counterexample to the without the little o1 case, then you could take a product and it would grow too fast. And for us, this little o1 is going to consist of log factors, so log 1 over epsilon squared, I think, subpower. So this is now our goal. So let me first kind of indicate what the removal has to do with the multicolored sum free problem. So suppose each point is in exactly one triangle. So we have disjoint triangles in both cases, except here our assumption is different, but suppose we actually have a multicolored sum free set. So then if you let delta n squared be the total number of triangles, then what you get is actually that m is the total number of triangles m is equal to both epsilon times n and to delta n squared. And then I claim that the two statements are basically equivalent. So, okay, so let's go one way. So suppose we have the removal lemma. So if we know that delta is at least epsilon to the 1 plus 1 over Cp, then in this case we can write that delta is equal to m over n squared and epsilon is equal to m over n. And so what this gives is that m over n squared is at least m over n to the 1 plus 1 over Cp. So this is kind of showing that the removal lemma implies the multicolored sum free bound, which if you then rearrange, so here we get n to the, if we move the n's to the left, we get n to the 1 over Cp minus 1 on the left, and we get that is at least m to the little cp on the right, and then cp is positive, so that's equivalent to saying that n to the 1 minus little cp is at least m. So this shows that the removal lemma implies the multicolored sum free problem, but this is also, you can also go the other way in the sense that if you start by knowing that m is at most n to the 1 minus cp, and you assume that each point is in exactly one triangle, then you can express epsilon and delta in terms of m and n and plug it in, and you get back the removal lemma. So in some sense, you can think of the multicolored sum free problem as a special case of this goal when our triangles are disjoint. And the reason this is useful is because then in the general case, we try to, let me save some preparation and then I'll explain why that's useful. So I'm going to concentrate on F2, and this is a bit simpler than what we originally had thanks to some observations of Lisa. So let's assume that our three sets are disjoint and that each point is in not much more than delta over epsilon times n triangles. So on average, we have delta n squared triangles and epsilon times n points. So on average, they're in delta over epsilon times n triangles. And let's assume that we don't have any points that are in much more. And then the basic idea is we take a random subspace whose dimension we've chosen carefully. And what we hope happens is that, so we intersect our three sets with this subspace, and we hope that delta and epsilon stays the same, so we have, except with this new n prime. So what we hope is that in this subspace, we again have epsilon times n prime disjoint triangles and delta times n prime squared triangles. And the way we've chosen n prime will be that delta over epsilon times n prime will be roughly 1. So then we'll be able to apply the multicolored sum free problem. And if you kind of believe me that it's equivalent in that case, then if you manage to keep epsilon and delta the same, then you can kind of guess that the balance must work out. So we take this subspace W, and we intersect our three sets. So now not every triangle will be kind of, so let's call a triangle in this cross product good if it's good for us. So basically, it doesn't intersect any other triangles. So we basically want to argue that in this intersection, we end up with a lot of good triangles. So specifically what we prove is that if we have a triangle in the original sets, then, and we take this random subspace, then if we condition on this triangle being contained in this subspace, the probability that it's good is at least 2/5, some constant, which for us is 2/5.
What does the word point here mean? Is like x prime by itself a point? Or the triple x prime, y prime, z prime is a point?
Yeah, I meant point as in x prime is a point, and y prime is a point, and z prime is a point. So basically, there's no other, I guess there's no need for primes there. So if x prime is not in any other triangles contained in W, y prime is not in any other triangles contained in W, and z prime is not in any other triangles contained in W. And let me try to briefly indicate why this claim is true. Basically, if we have, let's say, x1, y1, z1 kind of ends up in W, then we have some other triangles that contain x, say, so x1. So let's say we have x1, y2, z2, x1, y3, z3, and so on. And now you can, if you think about it a bit, you can convince yourself that if I know that this is contained in W, then the probability of this second one being contained in W, it's roughly n prime over n. Basically, so the point is once x1 is in W, it's basically independent whether these two are in W, and for each of them you need one more vector to be in W. So if x1 and y1 are in W, then z1 is automatically in W. And same if x1 and y2 are in W, and kind of for these three vectors, it's basically independent whether they're in W. And so then you can bound the probability, you can just take, so then condition on x, y, z being in W, you can bound the probability of any other triangle being in W as 1 over, basically epsilon over delta times n, and so you can get an upper bound here. Roughly what's going on is these, if you have all the triangles containing x1, it's basically pairwise. Once x1 is in your set, it's basically pairwise independent whether they're there, and we chose it carefully so that we expect one of them to be there. So then with positive probability, it will end up being 1. So then we can take a subspace of dimension D, which has roughly the same density of good triangles, and the good triangles form a multicolored sum-free set by definition. And so, it turns out, so we show that delta and epsilon stay roughly the same, this isn't how it's written in the paper, this is kind of what's going on there. We can apply the multicolored sum free bounds to get the bounds on epsilon and delta that we want. And then in the general case, you can delete points that are in too many triangles, and then we can make the sets disjoint, and we do this carefully, and epsilon and delta will not change significantly. And so this gets proof. Okay, so that's the basic idea of the proof for triangles.
So, I mean, can you give us a sense of how you get exactly Dirac constants? You mentioned that your thing actually matches previously known bounds.
Yeah,
But
so
it's
the
not-
previous...
It's not exactly clear from this why you end up having.
So the previous bound is actually, I mean, it's basically because the multicolored sum free bound is sharp. So, so this here kind of shows that the removal lemma implies a bound on the multicolored sum free problem, which then you can turn around to say that a lower bound on that implies a lower bound on the exponent in the triangle removal lemma. And
I didn't know that the thing that you're using is sharp because the.
so
Okay, yeah, okay.
what we lose is always, it always falls into this little one here.
Yeah, okay. No.
So that's, and then at the end we can get rid of it with the product argument. Okay, so now what's the proof for k-cycles? So let's try to copy the proof and then see where it goes wrong. So the first step was that we can reformulate it as saying that if you have so we have these k sets. We want to show that if we have a small number of k cycles between them, then we can delete a small number of points from each of the sets and get rid of all k cycles. We can reformulate it to say that if you can take a lot of disjoint k cycles, then you have a lot of k cycles in the product. That works perfectly. The product argument that gives you a little O1 here also goes through exactly the same. And the multicolored sum free result also extends to k. That's also fine. And however, then in this subspace sampling argument, we get into a problem. So here, just recall that what we had is that if we have two triangles that intersect in this point x1, then once you know that x1 is in W, it's independent whether these triangles are in W, basically. And as stated, this is true in F2 with the disjointness assumption, but you can add a few or I think it's p dummy coordinates at the end, and then it becomes true in FP. However, this fails in multiple ways if k is bigger than 3. So the most obvious way that it fails is you could have two k cycles intersect only in x1. You could have them intersect in x1 and x2, and then their joint probability of being in W will not be independent. They can for triangles, if they intersect in at least 2 points, then they must intersect in the third point because their sum is 0. But here, since k is larger, we don't have that. And it gets even worse because you can also have them intersect in a linear equation that's not a point. So for example, let's say k is at least 5, you could have two k cycles where x1 is equal to x1 prime, and then x2 plus x3 is equal to x2 prime plus x3 prime, and then the last coordinates are equal. And there are many complicated ways in which it can fail, and then sorry?
It's not that there is a small number of all of them. I mean, you lose 1 power of n.
So we didn't.
Because
So we didn't see a way to argue that this must be small just for any set of disjoint k tuples.
What are dummy coordinates?
What I meant is that you have triples in FP to the n, and then to the first set you add a coordinate that's, so you map it to FP to the n plus 2, where you add 1, 0 to the first one, 0, 1 to the second one, and then minus 1 to the third one.
So to make it tripartite.
Yeah, and then they become kind of independent linears.
So the multicolored sum free result is tight for K.
I'll get back to that later too. Okay, so this didn't work, so we found a different proof. Okay, so here's our goal again, and that should be a P, not a, or sorry, that should be a K, not a 3. So sorry about that. So the proof that we found actually works by induction on K, and it uses K equals 3 as a black box base case. So basically, the K equals 3 case used the multicolored sum free problem as a black box, and here we use the entire K equals 3 case as a black box base case. So let's let K be larger than 3. And as this is kind of the same as before, we can assume that each element is in at most roughly delta over epsilon times n to the k minus 2 k cycles again. And then we'll define alpha to be the k minus second root of delta over epsilon. So this is alpha to the k minus 2 times n to the k minus 2. And then what you would expect is that, so if you fix a single element, you have alpha times n to the k minus 2 degrees of freedom. What you expect is that if you then fix one more, you lose alpha n. If you fix two more, you lose alpha n again. If you fix three more, you lose alpha n again. And so then we will call an I-tuple of elements bad if it doesn't satisfy this, if it extends in kind of too many ways. So more than you would expect. And this is kind of also what causes problem with the other, where we tried to generalize the proof. So an I-tuple of elements is bad if it extends in too many ways to k seconds. And now, so I don't want to go into the precise arguments here, but you can maybe kind of guess that since each element does not extend in too many ways, if it is in some bad tuples, it shouldn't be in too many bad tuples because overall, on average, it's correct. And then what we do is we take a large set of k cycles. So by large set, what I mean is we don't lose anything in the exponent, just lower order terms, and a subset of the coordinates that's bigger than 1, and it has two properties. So first of all, for each of the k cycles in our collection, if you just take the coordinates with an I, this is not a bad I-tuple. And the second property is maybe a bit more complicated, but basically, so we can look at all the k cycles which sum to a fixed value over our set I, and this shouldn't extend in too many. There should be an n there. So this shouldn't extend, there should be an n to the k minus 2 there, sorry. So this shouldn't extend in too many ways as well.
K minus I.
No, so here I'm just fixing the sum, but I'm not fixing the specific coordinates. So this should be equivalent to fixing a single coordinate, fixing the sum of certain coordinates, or any linear combination. And I don't want to go into more details about how we find this, but it basically involves this D I mentioned earlier. And then what this allows us to do is apply induction where we just add up the coordinates in I and just make that a single new coordinate. So we end up with this k1, we end up replacing k with k1, and then we can take a large set of k tuples, epsilon times n k tuples, where the coordinates not in I are disjoint, and the coordinates in I are not necessarily disjoint, but their sums, the set of sums is disjoint. And then this allows us to apply induction to this set of K1 tuples. And I hope that you trust me that the math works out and this gives us a bound on CPK. Okay, so I should have mentioned here that the bound that this gives is basically, so big CPK is equal to K minus 2 times big CP3 minus K minus 3. Okay, so now what do we have in terms of lower bounds? So let's talk about the K multiplier sum free problem. So the definition, the problem is the same as 3 except for K, but let me just state it. So a K tuple of sets form a K multiplier sum free set of size n. If, again, you can kind of match up the elements into these K tuples, which are K cycles, and you have the property that there's no cross K cycles between them. And so the formulation of the upper bound proof that appeared on Terry Tao's blog extends to K, naturally. And so that gives an upper bound on a K multiplier sum free set in Fp to the n of size at most P to the 1 minus CPK times n, where this CPK is a positive number. And now for this one, as with the removal lemma, we assumed that this lower bound construction should also extend easily, but then when we tried to work it out, we also noticed that it hit similar challenges. So in their construction, they take a random map to another set. They also basically end up taking a random, they start with some set of 3 sets, and then they also end up taking a random subset, and they use the same property that if you have 2 triangles, they're either disjoint, they intersect in one point, or they're the same. And as before, for K larger than 3, this is not true. But here we were able to kind of get around this, and we can do a lower bound construction for an explicit CPK prime, which should be equal to the CPK on the previous page. Whether you're familiar with the story of the Kleinberg-Sullivan-Spire paper, there's a similar conjecture that should be true, and if it's true, then it's the same. And similarly, the upper bound proof actually works for CPK prime if they're not the same. And so there was a previous iteration of this paper where there was this upper bound proof, and that easily generalizes to K. So for the K multicolored sum free problem, we basically have a sharp bound and then modulo this conjecture for K. So now, what does that give for K cycle removal? So recall that this is the upper bound that we have. And in terms of CP3, it's what we have here. And I should have mentioned this earlier. So if you analyze it asymptotically, CP3 is roughly some constant times log p. So here, this then grows as k times log p asymptotically, some constant times k times log p. Now, as in the case of k cycles, lower bounds for the k multicolored sum-free problems imply lower bounds on removal, basically this same calculation. And so this construction gives a collection of size n to the 1 minus CPK. And so what this gives is that the optimal exponent is that, if you do the math, it gives that the optimal exponent is at least k minus 2 over little CPK plus 1. So the gap here is that basically this is CPK, and here we have CP3. And this is the ratio here is roughly log p. If you fix p and k gets large, this is 1 time. This grows as 1 times k, and this grows as log p times k plus lower order terms. Okay. So this brings me to further questions. The first question is, we have these bounds on CPK, and what is the correct value? So sort of, the upper bound that we get is sort of, if you could have as large a k multicolored sum free set as a 3 multicolored sum free set, then what would you get? So it's kind of, I guess the question is, if you go to removal, can you somehow use some magic to make to work with 3 multicolored sum free sets and combine them, or not? So this would be nice to nail down exactly. Another question is, if you have a subset of fp to the n, well, this was also mentioned earlier, if it has no 4-term arithmetic progression or no k-term arithmetic progression, how large can it be? I believe the polynomial method gives a trivial bound for 4 and worse than the trivial bound for larger k. And can you also get a removal lemma with good bounds? You can get some removal lemma, but can you get polynomial bounds? And more generally, you can just ask, you have k sets and multiple equations, what can you get? As I mentioned, a single equation, you basically just have one case, which is what we looked at, but for multiple equations, there are a multitude of possibilities. And finally, can any of these techniques help with the graph removal lemma? The one way this maybe contributes to that question is for the triangle removal lemma, you can adapt our subspace sampling argument by just sampling random vertices of the graph to show that if you can just prove this lemma called the diamond-free lemma, so the triangle removal lemma implies the following claim: if you have a graph and each edge is in exactly one triangle, then the number of edges is little o n squared. This is kind of the analog of the multicolored sum free problem, and our proof can be adapted to show that if you can prove that with good bounds, then you can also get a bound on the triangle removal lemma. On the other hand, this doesn't work for other graphs for the same reason that our k-cycles didn't work, and of course, you also need to prove something better for the diamond-free lemma then. And that's all, so I'll finish there. Thank you.
Questions?
Can you prove conditional results saying that if you have some better bound in the 4AP case, then you get something for removal?
I actually have not looked at 4AP. I don't know if either of you.
Yeah, I haven't looked at this. It's not the 4AP as much as the multicolor 4AP.
Yeah, it would have to be the multicolored 4AP. Yeah,
Seems
that's
plausible. I haven't checked this.
Is there any example of 2 equations, let's say, maybe 2 equations with many variables for which you could say something?
not that I know of. Seems like maybe this is, so I haven't thought this through, but it seems like for 4APs maybe it could work because you don't run into these issues. Because if they intersect in 2, then they must intersect completely. I don't know about the subspace thing off the top of my head, but
Is there anything different if you look at non-abelian group, like you want the product of the elements to be 1 over something?
well, I think for general groups, even abelian groups, it's not clear how to sample to a smaller group to get.
So I'm not talking about the proof, just are there any bounds for?
So the Carl-Saravena proof doesn't use abelianness.
Yeah. Okay, so
So-
you can redo, but there's nothing better than what you get from graph removal.
Yeah, I believe so.
Maybe it's these things from using triangles as black box, you could get equation 4 and equation 5. This works for graph removal also. So I'm knowing something for triangles, I want to get something for C5.
I think it's not, I think that's also not obvious. The basic problem is this subset I ends up being some subset of the coordinates. Now, if you have a K cycle, then it could be just some subset of the edges, and then it's not clear how to, whereas here, we do use abelianness there, I guess you could say. I think we don't know how to do that, right?
Yeah, we don't. We talked about it,
Yeah.
and there were problems with it, so, yeah.
Okay.
So,
It seems like it uses abelianness.
Right.
And so.
Other question? Okay, so let's check. See more 9:30 sharp. No,
somebody had.
Let's say you think for
Oh, yeah,
I saw
Then a small number of shifts. You don't
Yeah, I should like to about it. It's also sad. Although the students just had to meet them yesterday and they did some math theories after the bus.
Whoever said very intensity. Something like that because I think that that's
And so they're not those Oh yeah. This is without parts.
What happens?
So is the only case going to be when it's a square?
No.
Yeah, but like power of 4 is a square.
No, but we execute minus something factors as well. Any one variable polynomial factor.
It is, but that's not bad.
But that's not what
Can I ask a question? The theorem that you have about two relative points on a collection of lines is reasonable to expect that a kind of dual theorem for, say, 100 rich lines for a set of points. I don't want to say too rich lines, let's say really rich, some parameter rich lines through a set of points that agree not to many points in the lane.
Yeah, I guess you could make them on the last that's the one that's the
I mean, there's no, you can't use argument for this instruction, you can because it's still a reasonable.
You can tensor it up and then do some
Is there a way to dualize it? No. Yeah, well, okay, I guess you can have planes containing lines. That doesn't seem like a way.
We have a set of points. We want to know how many 100 rich lines there are. So is there a set of endpoints, most n squared 2 rich lines. There's still, at most, I guess there could still be n squared 100 rich lines, so there's a lot of them in a plane.
Right, but I'm forbidding that.
Yeah.
I was just thinking how the construction would work. If everything was in a plane, then we can dualize.